In this lesson, we're going to learn about what happens to our nuclear weapon detonation when the weapon casing is gone and it starts to interact with the atmosphere. Now, if you recall, in the last lesson on X-ray production, we had all that energy being produced by our fission chain reaction, which was contained in a relatively small area or small volume. So we ended up getting very, very high temperatures. This caused ionization of the material within the weapon. So now we have free electrons moving in all different directions, very high energies. We also have nuclei, and so our electrons are going to interact with the nuclei and they're going to produce X-rays via bremsstrahlung. So what we saw is these X-rays then go on to interact with other material within the weapon and the weapon casing itself. And the weapon casing, microscopic slice by microscopic slice, ends up getting ionized and basically vaporized until the point where the casing is now gone. So there's nothing actually containing all of that energy that we've produced via the fission chain reactions. So the only thing next to a weapon is going to be the atmosphere. Now, we'll talk about underwater and underground explosions a little bit later in the course. For right now, let's just focus on the atmosphere or air. So what happens then? Well, very similar to what we saw inside, where the casing got layer by layer, ionized and vaporized, this is going to happen to the atmosphere that's immediately outside the weapon casing. So you're going to have a wave of X-rays that's going to hit that atmosphere. It's going to fully ionize it, and then it becomes transparent to the X-rays that are behind it. And this is going to continue on for a bunch of successive layers. Now, while this is happening, we're expanding outwards, right? Because all of that energy, which is mostly in the form of these X-rays that we've produced, they're all going to want to just keep moving further and further away from the center of that detonation. So what we have is basically a rapid expansion of that dense energy core. Now, not only X-rays are being generated. Mind you, when the X-rays are interacting within the stuff that's in the casing, the core itself, the nuclear material, everything else inside of there, not all of it produces more X-rays. Some of the X-rays lose enough energy so that they can be absorbed by not fully ionized atoms that are still within this high energy density location. And these atoms, because the energy is not sufficient for them to become fully ionized, they're going to go into an excited state, and then they can lose that excess energy by emitting a photon of a very different energy and much lower energy. And this could be in the UV range, it could be in the visible light range, or it could be in the infrared range. Now, it's these atoms that are radiating quasi and visible spectrum photons. This is what we see when a weapon detonates. This is the visible light that occurs. And you can tie the visible light into the temperature of what's creating it. Now, if you had a magic camera and you could take a snapshot of a weapon detonation at 0.075 milliseconds after it starts to expand, what you would see is the temperature across this entire expanding sphere is approximately the same. It's about 1 million degrees. It's cooled down from what it was because as we expand, we start to lose energy through these multiple photon interactions. So the temperature goes down a little bit, but it's pretty uniform because it's happening very quickly. Well, what happens after that is that if we look at this second little line here on our diagram, we see this little transition point right here. And what this is telling us is that, okay, well, within a certain radius, we have a fireball temperature of a couple 100,000 degrees, about 300,000 degrees, right? And that corresponds to, 90 meters, we'll say, a little bit less. But if we look at 100 meters, the temperature is decreased much further than that, down to a couple tens of thousands of degrees. So right here. So what's going on? How can we have two different temperatures? Well, it has to do with how fast everything is expanding, the speed of sound in that local atmosphere, whatever height it happens to be, and the air getting compressed. So right up until this point, air is just getting fully ionized. We have outward pressure from this expanding core, but it doesn't really go anywhere, right? It's all expanding at the same time. So you're kind of having this pressure not really having anywhere to go. Now, once you hit basically a critical point called hydrodynamic separation, the amount of expansion or the rate of expansion of the core drops below a certain threshold. And that threshold happens to be the speed of sound in the medium. Once this occurs, you end up getting a pressure wave that starts moving away from the detonation point faster than the expansion of that inner fireball, that core. Now, once this happens, you see a temperature change, but it's not the temperature just doesn't go away. It doesn't drop down to the normal temperature of air. So why does this happen? Well, that's because as we apply this, incredible amount of pressure that we've generated within our weapon detonation, it basically starts smashing air into air, and you end up with something called shock heating. And this is simply by smashing molecules and atoms together. We're increasing their movement, so we're increasing their temperature, if you will. And what we end up seeing is not, the inner fireball that we've created, but we end up seeing the light that's being produced by this shock heating of the atmosphere. You'll probably ask, well, why don't we see the inner fireball? Well, as it turns out, the visible light, which is what we see from the inner fireball, is absorbed in the backside of that shock heated expansion front. So we have light being produced because we're superheating air by smashing it together really hard. But that pressure front has just the right properties that it's absorbing all of the visible light, most of the UV as well, and some infrared. It's absorbing it all, so it never gets past that shock front. So what we end up seeing is just the light from the shock front. And it's at a much, much lower temperature than that inner fireball. And so what we see in this figure, as we move out in time, we have this shock front that's racing much faster than the expansion of the inner fireball. And we see as it moves forward, of course, it's losing energy by this, the simple act of compressing the air in the shock front. So we see the apparent temperature of that fireball start to decrease. Now, again, it's showing here what the inner fireball temperature is, although there's no way we could really know that because anything that we try to put into place would get destroyed. Again, magic camera. So what we end up seeing is this apparent temperature when the shock front first separates, and it's got a lot of that pressure behind it. As it first separates, we're in, tens of thousands of degrees. But as we successively move forward in time, we see that it drops down to, 20,000. And then it drops down into the thousands of degrees at 28 milliseconds. And then if we look here at about 4 milliseconds, we've dropped down to somewhere about 3,000 degrees. This is all in Kelvin, by the way, the degrees, absolute temperature. So we've got now the internal fireball temperature is tens of thousands of degrees, but the outside one, the one we're seeing, is only about 3,000 degrees. And this is going to be important because when the temperature of that shock front drops down to this particular level, it no longer can absorb the photons that are being generated by that inner fireball. And so what we're going to see is that light starts shining through. So we end up seeing a much higher temperature than the shock front was producing. So and I'll show this on the next plot. So what we're going to see is the light, the temperature of the light, the apparent temperature of the light we're seeing from the detonation is going to go up, go down, and then go back up again. So We have the initial fireball before that shock front starts moving away from it and absorbing the light. So then now we're seeing that shock front producing its own light, but at a decreasing temperature, until it gets down to a certain point where it becomes once again transparent to that inner fireball, and then that light starts to shine through. So we have high temperature down to low temperature and back again up to high temperature. Now, one thing to note, the effects of nuclear weapons in the text, they kind of use X-rays and thermal radiation interchangeably. And it's basically because the thermal radiation is carried by photons, electromagnetic radiation of some sort. So it can be a bit confusing, but they're talking about the same thing, whether it be the X-ray heating or the visible photon heating, the shock front heating, all of that sort of thing. They use it interchangeably again. All right, so this is the plot I was telling you about. Now, the compressed atmosphere, as I mentioned, is opaque to the photons coming from the inner fireball. Now, there's something else that occurs here as well. Now, the real high energy, if you remember that Planckian distribution, we had the possibility of producing, photons in tens of keV. Now, these photons are, because they're so high energy, really aren't going to interact with the atmosphere all that much as they move outward, and they're going to run ahead of the fireball expansion, the X-ray driven fireball expansion, and they're even going to run ahead of the shock front. So what are they going to do when they're out there? Well, they're going to start interacting with the molecules of the air, but not to the full ionization. What they're going to do is they're going to provide some ionization and cause molecules that normally you wouldn't have thought of being there. Nitric acid is one of them. Nitrous oxide gets produced. Of course, we do have ozone that's already there. These molecules have a tendency to absorb light of certain wavelengths, of certain frequencies. And this is kind of important because there's a difference between what we should see based off of math and what we actually see. So let's go ahead and look at our little plot here. And we have this black line. This black line is supposedly the observed temperature that we should see just from shock velocity calculations. Okay, and this, by the way, occurs exactly at breakaway. So breakaway has already happened. Hydrodynamic separation has already occurred. Okay, so that's what we're looking at right here. So we're looking at the temperature of that shock front, not the inner fireball, not yet. Now, we see that it should be at pretty high temperatures, but if we look at the little dotted line down here, we see that this is what we actually observe. So why the difference? Well, about 8,000 to 9,000 degrees Kelvin, you're looking at sort of UV photon temperatures. Those UV photons are extremely highly absorbed by these molecules that exist in the atmosphere, but that we've also created as well. And moving down, as these high energy photons start interacting with the atmosphere, we don't see them because they're either scattered away or absorbed or something by molecules that existed and were created by the high energy X-rays that outran the shock wave. So instead of seeing this high energy, of 20 to 30,000 Kelvin, we only see about 10,000, a little bit less than 10,000, which is that cutoff for the absorption of the higher energy photons from, again, these nitrous oxide and nitric acid and ozone and some of the other weird chemical species that are created. So there's a big difference between what we see, the temperature that we see, versus what we calculate we should see. So we have here basically the height of the luminous output from our compressed shock wave. Okay, and then as it loses energy, we start to see a lower and lower temperature. until we get to this point right here. Okay, so this point is called breakaway. And it comes from the observers of the first nuclear weapon detonations, appearing to them that the shock wave, the opacity produced by the shock wave, that layers of it were getting torn away or broken away in very quick succession. So hence the name breakaway. Now what ends up happening from there is that the inner fireball, which is a different temperature, much higher temperature than the shock front at this point, starts to shine through. Again, the opacity of that shock front dissipates. And then so we see the apparent temperature of the fireball go up. Now, if you were looking at a detonation, which I don't recommend, what you would end up seeing is, from your perspective, is you would see just, a continuous fireball from the point of detonation, a continuous fireball that just kept expanding towards you. But you would notice that it was bright, really bright, and then it got dimmer, and then it got bright again. And that's all this diagram is showing you. And this diagram is very characteristic of a nuclear weapon detonation, the so-called double flash, because you see two different bright points that are created by the detonation. Now, some math estimate as to, okay, well, how big of the radius of the fireball do we end up with? And for atmosphere detonations and surface detonations, we have two different formula. There's a bunch of conversion stuff that's handled with the numbers that are in front there. I'm not going to ask you to kind of look at this. I just want you to know that it's there as an estimate. So what happens to these visible light photons? Again, we see some that are going to be absorbed as they go through the atmosphere by various chemical species. So we see here a simple chart that has the energies of these different photons. We have the radio waves all the way over to the left-hand side. We have infrared, we have visible, we have ultraviolet, and then we have temperature. And these temperatures are the same as those that Planckian distribution that we saw for the X-ray photons. Just looks a bit weird because we're on a log-log scale instead of a semi-log scale. So we see at a temperature of about 8,000 degrees Kelvin, we're peaking towards the visible spectrum with a fall off in the ultraviolet. If we looked at even higher temperatures, we'd see that they would start to peak into the UV range until finally we moved out of the UV and started into the soft X-ray range. Now the ultraviolet stuff, again, as I mentioned, it gets absorbed by stuff in the atmosphere, it gets scattered, and it never really goes anywhere. So we never see it. Once you get down into the visible light's not really absorbed as it goes through the atmosphere. It mostly has coherent scattering and Rayleigh scattering, if you remember from the lesson on photon interactions. So it just bounces around until it gets to an observer, our eyes. Now, the infrared photons that are created, again, as part of this detonation, if it's a clear day with low moisture content, these infrared photons can act pretty much like our visible ones. However, if we have vapor in the atmosphere, like water vapor, so cloudy or foggy or something like that, those infrared photons are going to preferentially interact with the water molecules, and then they won't make it, the energy they're carrying won't make it very far out either. It's the same sort of thing that happens when you heat up food in your microwave, right? The water molecules and the fat molecules inside your food preferentially absorbs those microwaves that are being emitted inside. And this happens with infrared and moisture as well. Okay, so what does this all mean? Well, it means that we interact with the atmosphere from our detonation. We basically create a shock front, which we're going to talk about a little bit later. That shock front carries the energy away from the detonation. It produces its own visible photons of a certain temperature because it's just mashing those the air molecules and atoms together pretty hard. This stops us from seeing the light from within the X-ray generated fireball, the center of the detonation, until it loses enough energy through basically expansion, spherical expansion and interactions, so that it no longer is opaque to that X-ray fireball, and then we start to see the light from that shine through. Now, the photons, this energy, these visible photons in infrared and some UV, but not really. Now, these things are still carrying a ton of energy, right? So what's going to happen to them? Well, when they hit something, they're going to interact with it. And they're going to deposit their energy in some way, either by straight absorption or through downscattering, similar to what we saw with the X-rays. And this is how we get thermal effects from our weapon. Now, I've got this cool little table here, which kind of shows some counterintuitive results. So we have different types of material. The effects are basically it catches fire, with the exception of aluminum, which can blister and bubble. And we're looking at how much radiant exposure, so how many photons carrying energy need to hit per centimeter squared. And the way the units they usually use is calories per centimeter squared. But again, it's just the energy of photons hitting per centimeter squared. And if you look at the smallest one here, 35 kilotons, paper will ignite at about 6 calories per centimeter squared from a 35 kiloton. But now if we look up towards 1.4 megatons, so 2 orders of magnitude almost higher, we find that it needs more radiant energy than it did for the 35 kiloton. And then if we go all the way up to 20 megatons, we see that it's more than double the amount that we needed with the smaller detonation. So what is going on here? How is that even possible? You would think bigger detonation, more radiant energy is being produced, so you're going to need less of it because it's higher energy than you would need for a smaller detonation. Well, here's why it's a little counterintuitive. So if we go back to this diagram, okay, this diagram is for about a 20 kiloton detonation. Now what happens as we increase our explosive yield, we're going to take this graph, we're going to take this plot line, and we're going to stretch it out over time. So we're having, a lot more energy being produced. However, because it's so powerful, it's taking a lot more time to go through that radiation and re-radiation and compression and shockwave moving forward. So we're taking this graph and we're basically just stretching it out. So what ends up happening is, we're producing more energy, but that energy is spread over a longer period of time, so that whatever we're depositing the energy into has time to get rid of some of it before it gets to that ignition or flammable point or blister point if it's in metal. So higher detonation, that energy, there's more energy, but it's distributed out over a much longer period of time. And that's what this table is basically showing you. So what we're going to do in the next lesson is we're going to look at how do we describe the thermal energy source of a nuclear weapon, and then how does that energy actually get transmitted through the atmosphere to things so that it can interact and deposit that energy. So that's it, and we'll see you next time.